The quiz problem for today was to attempt to linearize a set of data using the square root function and also using the logarithmic function, obtain the corresponding models, and decide which model was the better. So if we have this data, if we try to linearize it using a square root, and let's see why that might make sense, these numbers are increasing faster and faster. The increase here is about a little over 6, the increase here is about 10, the increase here is a little over 13. So it's increasing faster and faster, 6, 10, 13, almost a linear sequence, which suggests that maybe this could be quadratic data. And if so, then maybe it's an x squared type thing, and the square root function might possibly linearize it. So we take the square roots, and just taking the square root of the y values, the square roots of the y values, and then we kind of test to see how linear this seems to be. Difference here is 0.8, the differences here are 1.1, assuming I've taken the square roots correctly, and you ought to validate that. That could well be linear. On the other hand, it could well indicate an increasing progression, that the differences maybe seem to be increasing a little bit, and maybe it isn't quite as linear as we might hope. We can also take the logarithms of these quantities, and our x equals log y data gives us values 1.08, 1.26, 1.45, and 1.62 for the logs of y, and that gives us differences of 0.18, 0.19, and 0.17, which indicates that this might well be linear. There's no real pattern to the way these things fluctuate about the average value, which is 18. One's bigger, one's smaller. Of course, it's hard to establish a pattern with only 4 data points. If we had a large number of data points, then we'd find it much easier to see if there's a pattern here and if there's a pattern here. In any case, we try both functions because both seem to be reasonably well linearized. That is, we try both attempts to linearize because both of them seem to work out pretty well. Now what we have here is a graph of this data, the square root of y versus x. This column has square root of y versus x, and the data comes out something maybe like this. Actually, it's probably not a very good sketch of the data. Maybe it's not bad, but in any case, just an eyeball estimate of this, looking at the numbers, I estimated that this would be square root of y equals x plus 2.5. So if the square root of y equals x plus 2.5, then what can we conclude? Well, we can solve for y, and we get y equals x plus 2.5 squared. So you see we've linearized the data, or come close to linearizing it. We've gotten a model corresponding to the way we linearized it. We linearized with the square root of y, so we have the square root of y in our function here. We write down that model, the linear model for this graph, and we solve for y, and we get this model. So we're going to test this model and see how it works with the original data. Let's also look at how the attempted linearization with the logarithm function works. Okay, we have log y versus x. Here are our data points. They're very close to being linear. So we have log y is about 0.9 plus 0.18x. Now, we get this simply by making an estimate. So we see that the log of y equals 0.18x plus 0.9. That's a pretty good estimate to this linear function. Then we have y equals 10 to the other side. That is, if log y equals something, then y equals 10 to the power. And y then will be 10 to the 0.18x plus 0.9. And then using the laws of logarithms, that's 10 to the 0.9 times 10 to the 0.18x. And 10 to the 0.9 is 7.9. 10 to the 0.18x is 10 to the 0.18 to the x. 10 to the 0.18 is 1.51, so we have 1.51 to the x. And here's the model corresponding to the logarithm attempt. The attempt to linearize by the logarithm function.